One of the fastest anti-ship cruise missiles in the Soviet arsenal is air-launched and has a maximum range of 350 nautical miles and top speed of Mach 2 above 35,000 feet and Mach 1 at sea level. The threat is real. Defensive weapon systems are in place, awaiting a target vehicle that can replicate the threat posed by Soviet anti-ship cruise missiles into the 1990s. On its way to meeting that need is Firebrand, formerly known as the XBQM-111A Mach 2 class target drone. Designed to be either air or surface launched, this dual ramjet target is being developed by Teledyne Ryan Aeronautical under prime contract from the United States Navy, which calls for the delivery and testing of 6 free flight and 3 special test vehicles scheduled for completion by early 1982. Firebrand's ramjet engines are being developed and built under subcontract by the Marquardt Company. Rocket boosters, supplied by Thiokol Corporation, are similar to those used in the Patriot surface-to-air missile. Seen here in its 1/7 scale wind tunnel test configuration, Firebrand is designed to duplicate Soviet anti-ship cruise missiles in physical size, performance, radar cross-section, electromagnetic signature, and attack profiles. In its full-size configuration, Firebrand will have an overall length of nearly 36 feet, wingspan of over 8 feet, fuselage diameter of 28 inches, and ground launch weight with booster of approximately 6,000 pounds. From surface launch or C-130 air launch, Firebrand's basic mission profile begins with an initial rocket booster stage that takes it to supersonic speed, where its ramjet engines take over for an accelerated climb to the high-altitude cruise phase of the mission. Firebrand's high-speed dive brings it into the low-altitude over-the-deck simulated attack phase, which terminates in a pull-up just short of the target ship, followed by a brief climb to recovery altitude, where its drag and main parachute deploy. Firebrand's payload will include an integrated expendable emitter for the H, I, and J bands, an electronic countermeasure system, a passive and active radar augmentation system, and a scoring system. From our original proposed configuration, we came to realize several potential problem areas, which initiated 2 alternate configurations. The first wind tunnel test conducted at NASA Ames in December '77 and January '78 was to evaluate all 3 configurations, gather data, and select an optimum configuration. Prior to transonic wind tunnel tests in the Mach 0.9 to Mach 1.3 range, the selected test configuration was modified to incorporate a larger vertical tail and relocate the wings slightly forward. The CalSpan transonic tests confirmed changes made in the final configuration, which was then sent back to Ames for supersonic testing, successfully completed in July of this year. The final series of tests have been conducted at the LTV Wind Tunnel facility in Grand Prairie, Texas, with the Thiokol rocket booster to gather data in aerodynamic forces and trajectory and separation characteristics of the booster. Engine testing has encountered some technical problems in maintaining a stable and efficient fuel-air mixture over the wide speed-altitude envelope that the ramjet is required to operate in this application. Development has been slowed and is currently from 3 to 6 months behind schedule, but Marquardt is making steady progress toward Phase 2, flight weight testing. In the materials and structure area of development, we've established the structural load paths, structural arrangements, and materials thicknesses to meet strength and dynamics requirements. Avionics development is also well underway. We've taken the extensive data produced by the wind tunnel tests, as well as the structural and thermodynamic models, and incorporated them into this 6 degree of freedom simulator. Basic control laws have been defined to where we can air launch or ground launch the vehicle in simulation and fly it through its basic mission profile, refining terminal guidance control laws as we go. Avionics hardware development in conjunction with software development is going on in breadboard and brassboard development. The heart of the system is the AN/AYK-14 standard airborne computer being developed by the Navy for the LAMPS helicopter, the F-18, and other programs. Off-the-shelf elements, such as the Harpoon Attitude Reference Assembly and radar altimeter, are being utilized where possible to reduce program risk and development costs. With less than 18 months elapsed since inception of contract, Firebrand is on or ahead of schedule in most areas of development, with initial engine deliveries due in mid-1980 and full-scale contractor testing of the Firebrand vehicle to commence later the same year.